Welcome to session 2 of structural models. This is video 2.1. Okay, now last time we talked about, I told you to read the pages from green. We talked about a likelihood function. Let me do one quick thing. I probably should have done this last week, but it's useful to mention now. Okay, recall that we defined L of theta, big L of theta, equal to f of x1 theta times f of x2 theta, so on, all the way to f of x in of theta. Okay, assuming all the x's are independent. Now, by the way, so I told you each x sub I or x sub t is our set of independent variables and also our dependent variable. Now, our dependent variable, we like to think of it, includes an error term. And that error term is random. Therefore, so that means that the dependent variable is equal to some non-random stuff, the independent variables, plus some random stuff, the error term. So that means the dependent variable is a random variable. Okay, so now I wrote L of theta. I didn't write it as a function of these x's, but it is. Okay, but with that, so because it's a function of those x's, and those x's include a random variable, that means that this L of theta, our likelihood function, is a random variable. Okay, so we're going to talk about things like the expected value of L of theta, okay, the variance and so forth of that. Okay. Okay, that's coming very soon. Okay, now, next thing, I want to give you a definition. This is from green. I of theta, sometimes called the information matrix. Now, I told you at first to think of theta as just a scalar. So if theta is a scalar, that I is also a scalar. But if theta is k parameters, then that I is going to be k by k. Okay, so the information matrix, scalar, whatever we want to call it, is defined as equals negative the expected value of the second derivative of log of L of theta. The expected, okay, and that's on page 133, okay? Now, the important thing, remember that this L of theta, as I just told you, that is a random variable, okay? So that means we take some sort of transformation of it, log of theta, or take some sort of operation on that, the second derivative of that. All of that stuff is still a random variable, so still, for that reason, it makes sense to talk about the expected value of it. Okay, now we take the negative of that. Okay, remember that will come in handy once you're doing your homework. If you forget to take the negative of something, what you're going to end up happening is getting your variance of something is negative. We know that the variance has got to be positive of any random variable. Okay, now, I'm not going to go through the proofs. I wanted you to see them, though. So I want you to read them. You don't have to fully understand them, but I wanted you to see them at least once. It's from those green pages. For now on, we're just going to talk about some special properties of the maximum likelihood of a maximum likelihood estimate. So the estimate we get when we maximize the likelihood function. So I'm just going to show those properties now. So, but you have the pages from green. You know that some smart people have proven why that we have these special properties. Okay. Now the key special property. Okay. Now remember, we talked about theta hat. We talked about theta hat is the value of theta that maximizes L of theta. So therefore, it's also the value that maximizes the log of theta. By the way, don't forget that information matrix. You got to take It's the log of the likelihood. Now, you're going to do a homework problem where you're going to have to compute this, and it's easy to forget to take the log. Okay, that one little typo, you forget the ln, and all of a sudden your homework problem is going to be completely wrong. Okay, theta hat is what maximizes, is the theta that maximizes that. Now, we're going to assume it's unique for now, okay? So theta, that's the thing that maximizes it. And by the way, so that's what we get when we set the derivative equal to 0. Again, that's just a transformation of L of theta. L of theta is a random variable, which means this theta hat, it's going to be a function of all that stuff, of the rand x1, x2, and so on. Theta hat is going to be a random variable. Okay? So because of that, we can talk about its distribution. And what we have, this is on page 137 in green. There's some properties that some very smart people have proven that theta hat is asymptotically distributed as normal with mean theta, variance I of theta to the -1. Okay, so, and this is, by the way, put an A here. So that means theta hat is asymptotically distributed. Okay, so that means in the limit, as that n approaches infinity, so as we get infinite data, theta hat is going to be distributed normal, okay? When we get infinite data, okay, so it may not be exactly normal in finite samples, but it's going to get arbitrarily close to this being true as n gets larger and larger. So as n gets larger and larger, this is going to be a better and better approximation for being true. That is, that theta hat is distributed according to this. Okay, so theta hat, first, we can show that this thing will approach 0. That variance is going to approach 0 as we get infinite data. So that means that theta hat is going to approach theta. So that means it's consistent. We have a consistent estimator. That means consistency means if you have infinite data, you're going to eventually reach the truth. Okay, you're going to get arbitrarily close to the truth as you get bigger and bigger data, bigger and bigger sample sizes. Okay, so sometimes I joke, what's the problem with infinite data? The answer is it takes forever to collect it all. Okay, that's a joke. You get it? We always say it takes forever. It literally would take forever in this case. Okay, that is the key thing I wanted you to see. Okay, so I want you to remember that. We've got this theta hat. That's going to be our estimate. Theta hat, that's going to be a random variable. In the limit, it's going to be distributed normal with mean equal to the truth. The truth is the true theta, okay? With with variance, the information matrix, the inverse of the information matrix. Now, by the way, one final thing, okay? So we're going to need to do like statistical tests, hypotheses on this theta hat. We'll estimate theta hat by maximizing the likelihood function. We'll get a value of theta hat. And we want to know, or we might have a null hypothesis that theta hat, or that theta equals 0.6. Okay, suppose theta hat equals 0.667 or something. So, can we reject? We have to know the variance. Okay, the variance is a function of the true theta. We don't know the true theta. That's something that nature has chosen, but nature does not tell us. We can only estimate what is the truth. Now here, Green has written, I don't have the pages, it says that Kramer in 1948, so we're using some results that are very old, more than 70 years old, has shown that theta hat is a consistent estimate of theta. Okay, now then there's some other results. It says if you take some sort of function of that theta hat, and that function is continuous, and I think it's got to be the slope is never infinite, nor the values. The values have always got to be finite. It's bounded. There's some technical assumptions on this. If all of that is true, then for any function, I've already used f. Let's call it a g. Let's call it h. H of theta is a consistent estimate of h theta, as long as that h has those nice properties, that's continuous, bounded, slope is bounded, and so on. Therefore, I theta hat is a consistent estimate of I of theta. Okay, so we don't know I of theta, but what we can do is we know I, and that's just going to be this function, the second derivative of that. Let's see, we're going to have the expected value of that. Anyway, well, we're going to have to ignore that e for a second. Okay, what we will do in practice is we'll just take the second derivative. And the second we'll call it the Hessian matrix. That's why it's called big H. We'll take the negative of that, then we'll take the inverse of that. We can have a computer do all these calculations for us to do that. Once we do that, we'll just take the negative of it, take the inverse of it, and we'll know that H of theta hat is a consistent estimate, okay, or call it I of theta hat is a consistent estimate of what we want. So we're just going to substitute I of theta hat for that value. In particular, we get that from H. We want to take H, the negative of it, and then actually once we substitute H in there, we'll then eventually take the negative 1. That will tell us the variance. Once we have that, we can use, what this says, we can use theta hat, even though we don't know theta. Okay, nature has not told us that. We can use theta hat as a consistent estimate of the variance, and we can do statistical tests with that. Okay, so that's where we're going. Okay, that is video 2.1. See you in 2.2.